Okay, so I will start sharing. So it is visible. Essentials of pharmaceutical chemistry. Is it okay? Is the module visible?
Yeah, it is visible, sir. You can
Okay,
continue.
I will start with the pharmaceutical chemistry. So, inorganic pharmaceutical chemistry is a science that makes use of laws of chemistry to study inorganic substances as drugs. And what about drugs? Their preparation, chemical nature, composition, structure, and other things. This unit presents the basic concepts of pharmaceutical inorganic chemistry with emphasis on description, mechanisms, and use of various pharmaceutical products which are clinically used to correct various body disorders. What are the objectives of this unit? Understand the various concepts of acids and bases and their importance in pharmaceutical chemistry. Explain the role of buffers in pharmaceutical preparations, their mechanism of action, and buffer systems present in the body. Discuss importance of various intra and extracellular electrolytes present in the body fluids, and list various inorganic preparations used to correct the diseased conditions of the gastrointestinal tract along with their mechanisms of action. So first we will start with acid and bases. You may have studied about acid and bases in your previous classes. We are summarizing the theory of acids and bases here to enable you to recall it. This will help you in understanding the unit. So, what are RNAs, bases, and acids? RNAs defined an acid as any compound that releases protons H plus in water, and the base as any compound that gives OH minus ions in the water. So RNAs acid and RNAs bases. Acids give H plus and bases give OH minus. Now, according to Bronston-Lowry acids and bases, according to the second definition proposed by Bronston and Lowry, an acid is a proton donor and base is a proton acceptor. Proton is H plus, so acid is H plus donor and base is H plus acceptor. Then Lewis acid base. The Lewis model of acids and base proposes that an acid is an electron pair acceptor while base is electron pair donor. So it is opposite to the previous definition. In this, the acid is an electron pair acceptor and base is electron pair donor. Now, what is pH concept? To speak of acid or base strength, we need scales of acidity and basicity. The pH and pOH scales are quantitative representations of this value for acidic and basic solutions. A very convenient concept called pH was proposed by Sorensen. He defined pH as the negative log of hydrogen ion concentration. It can be expressed as by the relationship that is pH is equal to negative log of hydrogen ion or minus log H plus ion. The prefix P in the front symbol takes means that take the negative log. For example, if the pH of log 10 to the power minus 3, then pH will be 3, which is highly acidic. Similarly, pOH will be minus log OH ions concentration. Just as H plus and OH ion concentration in a solution are related to each other, so also are pOH and pH. From the equilibrium expression for the dissociation of water, log Kw is equal to log H plus and log OH minus. So pKw is equal to pH plus pOH, and pH plus pOH together when added comes to 14. So pH plus pOH will always come to 14. Now pH, according to pH, we can describe acidic and basic solution. If the pH is less than 7, then it is an acidic solution. If the pH is around 7, it is neutral solution. And if the pH is more than 7, it is basic solution. Now we come to buffers. A buffer solution is an aqueous solution consisting of a mixture of weak acid and its conjugate base, or a weak base and its conjugate acid, whose pH does not change on addition of small amount of an acid or base. So buffers do not change their pH values also on standing for a long time or exposure to atmosphere or slight dilution with any acid or base. So buffers can be weak acid and its conjugate base, or weak base and its conjugate acid, from which pH does not change. Thus, a buffer systems are pairs of related chemical compounds capable of resisting large changes in the pH of a solution caused by the addition of small amounts of acids and bases. The buffer should not react with other chemicals in a pharmaceutical preparation. Also, it should not participate in redox reactions, that is, reduction and oxidation reactions. Any chemical reaction which involves oxidation and reduction, that is, redox reaction, alter the solubility of other components, form complexes with active ingredients, or participate in acid base reactions other than those required as part of buffer function. So these are the basic features of a buffer solution. The pH of blood is human body is 7.3 to 7.4, which is controlled by buffering mechanism. Now, roles of buffers in pharmacy. First one and most important is solubility. The pH plays an important role in the solubility behaviors of the compounds. The required pH gets adjusted by buffers. Many inorganic salts such as ferric, phosphates, borates become soluble in acid media but precipitate in alkaline media. Many organic compounds with acidic functional group are soluble in alkaline media, and similarly, amines and alkaloids are soluble in acidic media but are almost insoluble in alkaline media. So we can see that the buffers and its pH plays an important role in the solubility of the compounds, whether it is acidic or whether it is alkaline. Now the color of many synthetic and natural dyes is pH dependent. Red color of cherry and raspberry is maintained in acidic pH and becomes pale yellow to nearly colorless in alkaline pH. So not only chemical or the pharmaceutical products, also the natural products like fruits are also maintained by the pH. Then stability of some compounds to redox conditions. So stability of compounds in redox reactions is also one characteristic. Patient comfort: an extremely acidic or alkaline pH must be avoided to prevent tissue damage. So extremely acidic or basic solution can damage any body tissue. Now, intra and extracellular electrolytes. What are these? These are various inorganic compounds present in the body fluids, and the concentration of these in various compartments is balanced in such a way that the body cells and the tissues always have the same environment. Some regulatory mechanisms controlling the ionic balance, osmotic balance, and pH, which in turn maintain the concentration of solutes in various body fluids and other parts of the body. Generally, in the body, the electrolyte concentration is maintained, but if the body cannot maintain or correct the electrolyte balance, then it is done by external administration, which is known as replacement therapy by various drugs and various supplements. Various products like electrolytes, acids and base, carbohydrates, proteins, amino acids, and blood products are used as replacement therapy as per need of the patient when the balance of the fluids is disturbed. In this unit, we are going to consider the electrolytes used in replacement therapy and for correction of acid-base balance in various body fluids. Now, there are two compartments in body fluids, extracellular and intracellular. Extracellular fluid is the fluid found outside the cells. Extracellular fluid makes approximately 20% of the total body weight. ECF consists of blood plasma, interstitial fluid surrounding the cells, secretory fluid, which is fluid in transit, and dense tissue fluid, which is water located within dense connective tissue such as cartilage and bones. Intracellular fluid is the fluid inside the cells of the body. It makes up around 35 to 40% of the total body weight. So major physiological ions are chlorides, phosphates, bicarbonates, sodium, which is an extracellular fluid compound, and potassium, which is majorly situated in intracellular cation. Calcium, 99% of body calcium is found in the bones, and magnesium. So these are the main physiological ions: chloride, phosphates, bicarbonates, sodium, potassium, calcium, magnesium. The role of major physiological ions. The major role of physiological ions is to control osmosis of water between body compartments, to maintain the acid base balance needed to perform normal cellular activities, and to generate action potentials and gradient potentials, and control secretion of some hormones and neurotransmitters. Now we can use various electrolytes for replacement therapy, such as sodium replacement therapy, potassium replacement therapy, calcium replacement therapy, and others. Now, physiological acid-base balance, how it is maintained in the body. Acids, either as carbonic acid from carbon dioxide or lactic acid from anaerobic respiration, are constantly being produced during the metabolism. Since most of the reactions occur only within a very narrow pH, that is 7.38 to 7.42, the body utilizes several buffer systems. Two of the major buffer systems in the bodies are bicarbonate carbonic acid buffer found in plasma and kidneys, and monohydrogen phosphate dihydrogen phosphate found in cells and kidneys. So the major buffer solutions used to maintain the pH of the blood and other body fluids is bicarbonate buffer and monohydrogen phosphate buffer. If the body can restore the pH back to 7.35 to 7.45 by alteration in the respiration and kidney function, it is referred to as compensated metabolic acidosis or alkalosis. So, in major conditions, it can be compensated metabolic acidosis or alkalosis. Now, electrolyte combination therapy. There are usually two types of solutions used in replacement therapy: a solution for rapid initial response and a solution for replacement, subsequent replacement. So, we can use either Ringer's lactated Ringer solution, or oral electrolyte solution. Now, gastrointestinal agents. The digestive system in the gastrointestinal tract, which is a group of organs extending from esophagus to anus. Whenever the above functions go wrong, there are possibilities to occur disease or undesirable conditions. For example, when there is inadequate secretion of acid in the stomach, this causes achlorhydria or hypochlorhydria in the stomach, means acid decreases in the stomach. Whenever excess secretion of acids take place in the stomach, it causes the imbalance of acid enzyme ratio, finally leading to hyperacidity and even ulcers in the stomach. There may be accumulation of toxic substances or gases. Then there may be inadequate absorption of fluids and minerals from large intestine, thereby causing diarrhea. There may be insufficient peristaltic movement of large intestine, causing constipation, and there may be possibilities to occur ingestion of poisonous substances accidentally or intentionally. Drugs for gastrointestinal tract. It is possible to correct the above condition by administration of suitable drugs, which include products for altering gastric pH, protectics for intestinal inflammation, and cathartics or laxatives for constipation. Now we can divide products of altering gastric pH as acidifying reagents or acidifiers. The most common used acidifying agent is dilute hydrochloric acid. In case of a condition where acid has been decreased, we can increase the acid concentration by using dilute hydrochloric acid. Then there are some antacids. These are used in extremely acidic condition or hyperacidity of the stomach. The antacids also provide symptomatic relief from pain by neutralizing the excess of HCl and help in reducing pain due to ulcers. Now, protectives and adsorbents. These are chemically inert substances which are used in the treatment of mild diarrhea or dysentery or other GIT disturbances. Now, protectants or protectives are used to form a protective layer on the painful ulcers in the GIT, like bismuth compounds, and last one is cathartics, purgatives, or laxatives. In normal conditions, defecation occurs by peristaltic movement of the intestine, which occur about 3 to 4 times a day. Ignoring the urge to defecate and other factors like weakness of intestine, intestinal spasm, injury, diet, or as effects of other drugs leads to constipation. In this condition, the fecal material becomes dry and hard, and the use of laxatives or cathartics and purgatives provides relief in the constipation by retaining fluid in the bowels and are defined as cathartics. Cathartics are the drugs which bring about defecation, and they are used for treating constipation and for expulsion of intestinal parasites. They may also be given for clearing bowels before surgery. Then purgatives. These are also cathartics which act similarly but have mild action. Then laxatives. These are mild types of purgatives. These compounds act by four different mechanisms. They can be stimulants, in which the drugs which act by local irritation on intestinal tract and bring stimulation of the peristaltic activity in the intestine. Then bulk purgatives. These are able to increase the bulk of the intestinal contents, and these are cellulose or non-digestible types of material which swell considerably when wet and stimulate peristalsis as they increase the bulk of the stool. Lubricants. In constipation, contents of intestine become hard because of absorption of water by body, resulting in difficulty in clearing the bowels. The substances like liquid, paraffin, glycerin, mineral oils are acting as lubricants to provide relief. Then saline cathartics. These act by increasing osmotic load of intestine by absorbing large quantity of water and thereby stimulating peristalsis. Now we come to topical agents. The term topical means pertaining to a particular spot. Topical agents are the compounds that act locally on the body surface like skin and mucous membranes. A classification can be protectives, adsorbents or demulcents, emollients, astringents and caustics. So there are protectives, adsorbents, emollients, astringents and caustics. Now we'll come to Unit 8, Essential of Pharmaceutical Chemistry Part 2. Now, in this unit, you will learn about fundamentals of organic pharmaceutical chemistry. Till now, we were talking about inorganic pharmaceutical industry. Now, we'll talk about organic chemistry. You know that most of the drugs are organic compounds, and to understand their nature, it is essential for you to be familiar with the functional groups present in the organic compounds. So, after studying this unit, you should be able to Identify the functional group present in an organic compound. Give IUPAC names of various aromatic compounds. List various types of isomerisms in organic compounds. Write cis trans ZE isomers of a molecule. Assign the configuration of a chiral center as R or S, and explain the significance of stereochemistry in a drug. Now, functional group classification. We know that there are millions of organic compounds. Therefore, it is very difficult to study each and every compound individually. Thus, by grouping similar compounds together in a class or family, it is easier to understand their properties, reactions, etc. One way of classification is based on the functional group. What is a functional group? A functional group can be defined as an atom or a group of atoms in a molecule which exhibits characteristic chemical properties. For example, alkane with no functional group, alkene with an ethylene type of functional group with a double bond, alkyne with a triple bond, cycloalkanes, which are organic compounds, aromatic compounds, alcohol with OH group, phenol with a aromatic compound with OH group, ether with an O group, aldehyde with CHO group, ketone with a CO group, carboxylic acid with COOH group, ester with COO group, anhydride with COO group, amine with an nitrogen group, imine with an NC group, nitrile with an CN triple bond group, nitro compounds with NO2, amide with CON group, halide with a halogen, acyl halide with COX halide, thiol with the SH group, and sulfonic acid with SO2OH group. Now, nomenclature of aromatic compounds. In this section, we shall discuss some of the rules adopted by IUPAC, that is International Union of Pure and Applied Chemistry, for naming the aromatic compounds. The aromatic compounds can have any of the following types of basic skeleton. Compounds containing one aromatic ring, that is benzene and its derivatives. Polynuclear hydrocarbons having many polynuclear hydrocarbons, and heterocyclic compounds. So it can be anything. Now, first, compounds containing one aromatic ring. This class includes benzene and its derivatives. The derivatives of benzene include the compounds which can have any of the functional groups discussed before attached to a benzene ring. So it can be a chlorobenzene, a nitrobenzene, or a propylbenzene. So a benzene with a functional group and its derivatives, the compounds come in this group. Then desubstituted benzenes means many isomers of ortho, meta, and para. If it is in the first group, it is called as ortho. If it is in the second carbon atom, it is meta. If it is third or the opposite atom, it is called as para. Now, polynuclear hydrocarbons. It is in a polysubstituted benzene, the ortho meta para nomenclature is no longer applicable. So there may be many benzene rings attached to one another. These are called as polynuclear hydrocarbons. Then heterocyclic hydrocarbons. Aromatic compounds containing heteroatoms such as O, N, or S in the aromatic ring are called as heterocyclic compounds, such as this. In this, the benzene ring, there is one nitrogen attached in the sixth group, and OH is attached in the fifth group. So these are different types of heterocyclic aromatic compounds, hydrocarbons. Now we come to international non-proprietary names. International non-proprietary names are selected by national or international nomenclature committee. The WHO strives, the World Health Organization strives to provide one name for a drug throughout the world. While selecting an international non-proprietary name, the following points should be kept in mind. It should be distinctive in sound and spelling. It should not be similar to any other drug. It should not be too long. It should show relationship to substances with same pharmacological action. It should not conflict with any existing common names, and the patient should not be confronted with names that are likely to have anatomical, physiological, or pathological connotations. Example, a name starting with cancer would be acceptable. No. Common stems have been created to show the relationship to other substances of similar pharmacological actions. These are like AC. If any drug has AC in its suffix, it is anti-inflammatory, such as ibufenac group. Actide, synthetic polypeptide with a corticotropin-like action. And similarly, there are various stems to show different actions in the body. Now, isomerism. An important topic is isomerism. Compounds that have same molecular formula but different chemical structures are called as isomers. So the formula will be same, but the three-dimensional structure of these compounds is different. These are called as isomers. The phenomenon is called as isomerism. Isomers can have different chemical, physical properties and biological properties also. It is possible to classify isomers into various subtypes as shown. Constitutional isomerism are those compounds which have same molecular formula but have different bond connectivities. The sequence in which their atoms are bonded together is different. On the other hand, stereoisomerisms are those isomerisms which have the same connectivities of atoms but the spatial arrangement is different. So, according to this, constitutional isomerism can be further divided into chain isomerism, position isomerism, and functional group isomerism. And stereoisomerism can be further divided into conformational isomerism and configurational isomerism, which can be further divided into geometrical isomerism and optical isomerism. Some example of constitutional isomerism: chain isomers like butane and 2-methyl propane. So the molecular formula is same, C4H10, but butane is having a single chain and 2-methyl propane is having a branch chain, different in the chain length. Then position isomers, same formula, but the chloride group is attached to a different carbon atom. Functional group isomers like ethanol and methoxymethane, in which the oxygen group is present in the between. It needs to be mentioned here that the constitutional isomers have different physical and chemical properties than stereoisomers, which is more important, like configurational isomerism and conformational isomerism. Configurational isomerism, the absolute configuration of a compound, can be defined as the arrangement of groups in space. This type of isomerism is exhibited by those stereoisomers which cannot be converted to each other without breaking of bonds. It can be further classified into geometrical isomerism and optical isomerism. Then the next one is conformational isomerism. Arises due to different spatial arrangements of atoms or groups in a molecule which are obtained by rotation about single bonds. So geometrical isomerism is like cis and trans 2-butene. Cis-2-butene, in which the methyl group is in the same side, and trans-2-butene, in which the methyl group is in the opposite side. So this is a type of geometrical isomerism. The position of the carbon atom is different. Now, optical isomerism. Optical isomerism is depicted by optical isomers. Optical isomers are the stereoisomers which show optical activity. You may have studied optical isomerism in your BSc classes. There are many such molecules in which carbon atom is linked to four different substituents. Optical isomers are molecules that are non-superimposable mirror images of each other. Such isomers are called as enantiomers, such as enantiomer of 2-butanol. It is similar looking, but they are not super they are not superimposable mirror images in which there are different positioning of the different molecules. Designation of configuration can be R or S in this type of algorithm. The term configuration at a particular stereo center refers to the actual arrangement of the substituents in space. Thus, the enantiomers or optical isomers differ from each other in their configuration around the central atom. The absolute configuration of a particular molecule can be assigned according to RS system, R or S configuration. The R configuration in which the R is rectus and it is on the right side. So it configures in the right side, right type of clockwise motion. And S is from sinister, a Latin word meaning left, in which there is anti-clockwise or left side movement. So R and S isomers. Then significance of stereoisomerism. Thalidomide tragedy. You must have heard about a thalidomide tragedy in the past. Thalidomide, a non-barbiturate central nervous system depressant, was marked first in West Germany 1956. It found worldwide acceptance as an effective hypnotic, having no morning hangover by other countries like UK, Japan, Canada, and Sweden. The thalidomide was consumed by a large section of expectant mothers to ward off morning sickness, the unpleasant effect of early pregnancy. But Dr. McBride, an Australian, reported the association between thalidomide consumption and congenital deformities in the fetus. Babies with malformation of limbs were born to the mothers who consumed thalidomide during pregnancy. It was reported in 1970 that R isomer of thalidomide was favorable sedative effect, while S isomer causes prenatal deformities. So this is one example of difference in properties of S and R isomers. Now, activities of isomers of different drugs. Thiothezine, that is cis, is active. Thiothezine trans, that is inactive. Similarly, morphine, opioid analgesic, if it is minus, naturally occurring inactive, and morphine in which isomer is positive, synthetic and devoid of activity. Similarly, there are different compounds and their activity, whether it is active or inactive. Now we come to the ninth unit, that is concept of synthetic drugs. Pharmaceutical industry is concerned with the discovery and synthesis of compounds for biological evaluation as potential new drug therapies. It embraces the identification, design, synthesis, isolation, and chemical characterization of such compounds. Objectives of this unit is describe the objectives of synthetic medicinal chemistry and its development, describe the various advantages of synthetic drugs over natural drugs, describe the importance of structure activity relationships in pharmaceutical chemistry, and discuss the structural activity relationships and QSAR. Importance of pharmaceutical chemistry. The primary objective of medicinal chemistry is the design and discovery of new compounds which can be used as drugs. The discovery of a new drug requires not only its design and synthesis, but also the development of testing methods and procedures which are required to establish how a substance operates within the body and acts as a drug. So, we will mainly be studying about the objectives of medicinal chemistry in the designing of the new drugs. So, drugs are chemical substances that are used to prevent or cure diseases in humans, animals, and plants. The activity of a drug in its pharmaceutical effect on the subject and its acts by interfering with biological processes. So, no drug is completely safe. No allopathic drug is completely safe. It will have some pharmacological effect in the body, like pharmacokinetics and pharmacodynamics, both will happen. New drugs are constantly required as the strains of microorganisms are developing resistance to the existing ones. That's why they are also required for the improvement in the treatment of existing diseases and for production of safer drugs by reducing or removing the adverse effects. Now, types of drugs: drugs from natural products and drugs from synthetic products. First, natural products. Since time immemorial, the world has been using a wide range of natural products for medicinal purposes. These products, obtained from animals, vegetable, and mineral sources, were sometimes very effective. Early use of medicinal dates back to 7th BC, wherein the Assyrian herbal by of 7th century BC gives a list of medicinal plants. Similarly, Chinese Emperor Shen Nung described use of herbal medicines. Eber's papyrus from Egypt arranged medicinal plants in 1550, and even in India, they were using many Ayurvedic natural products to cure various diseases. Synthetic drugs. This wide range of pharmaceutically active compounds from the plants was used as the starting point for the development of drugs. The origin of many drugs must be looked for a substance of a biological nature, and in particular in the alkaloids. So, the origin of many drugs must be looked for in substances of a biological nature, and particularly in and the alkaloids. The elucidation of their structure has been a starting off point for chemists to synthesize similar compounds. Now, there can be cocaine, atropine, and morphine are particularly good examples in this respect, since substances which are made like them have shown clinically local anesthetic, antispasmodic, and marked analgesic properties, respectively. Today, many discoveries start with biological testing by pharmacologists of the potential sources in order to determine the nature of their pharmacological activity as well as their potencies. Now, once a screening program has identified substances of pharmacological activity of interest, the compound responsible for its activity is isolated and used as a lead compound for the production of related analogs. So, before coming into the market, the drugs passes through various stages: stage 1, stage 2, stage 3, stage 4 stages. The compound on which the development is based are known as lead compounds, while the synthetic compounds developed from a lead are called as analogs. Advantages of synthetic drugs. Synthetic drugs have the following advantages. Useful plant compounds are often easy to synthesize. No dependency on plant collectors or growers as a source or the long term survival of the plant. Synthetics can be patented, natural compounds cannot be patented. These are some advantages of synthetic drugs. Now, structure activity relationship. What is structure activity relationship? It is a means by which the effect of a drug or toxic chemical on an animal, plant, or environment can be related to its molecular structure. A structure activity relationship relates the features of a drug or chemical structure to a property, effect, or biologically active associated with that substances. So, depending upon the structural activity relationship, there can be different properties and effects in the body. It constitutes a part of medicinal chemistry wherein the modification of the effect or the potency activity of the bioactive chemical compounds is carried out by changing their chemical structures. Computer based modeling methods relating chemical structure to qualitative biological activity, structure activity relationship, and quantitative biological potency, that is quantitative structure activity relationship, have been applied in many diverse problem settings. What are the importance of SAR, structure activity relationship? SAR is located at the intersection of biology, chemistry, and statistics as depicted in figure 9.1. The focused interlinking of these disciplines has brought about the development of a research activity resembling the science of structural activity relationship. So, SAR is a conjunction of chemistry, biology, and statistics of various drugs. So, it may be combination of theoretical, experimental, and empirical chemistry. In relate in relation to structure to activity, the main aim of SAR is to develop an understanding of a class of molecules that are active, to find out what determines relative activity, and to know what distinguishes these from inactive classes. SAR includes the activities ranging from use of expert judgment to considerations of similarity, diversity of chemicals, to formal mathematical associations of properties and activity measures. So, not just physical properties, chemical properties, its uh, biological properties are also measured and distinguished in this SAR. So, depending upon the structural activity, we can classify different drugs according to their various properties and various functions in the body. Quantitative structure activity relationship. The fundamental assumption in quantitative structure active relationships is that similar chemicals have sufficiently common mechanistic elements. Quantitative structure activity relationship is development of a relationship between structural features and the property of interest so that property values can be predicted for new candidate structures. These properties include measures of potency, strength of binding of drug to an active site, inhibition of enzyme, and prediction of ADMET properties, that is absorption, distribution, metabolism, excretion, and toxicity. ADMET properties and absorption of the drug, distribution in the body, metabolism in the body, excretion from the body, and toxicity caused by excessive consumption of the drug in the body. Then 3D QSR, structural activity methods that consider the 3D structure of model compounds in spatial relationship to one another are collectively termed three-dimensional quantitative structure activity relationship methods. Now we come to last unit of today, that is pharmacognosy and phytopharmaceuticals. First, the introduction. The present chapter deals with the term pharmacognosy, its origin and history. It also covers the study of phytoconstituents, different aspects of classification of phytoconstituents, their extraction, isolation, and characterization by using different physical, chemical, and spectroscopic techniques. Pharmacognosy is concerned with the knowledge of crude drugs obtained from natural origin. Pharmacognosy has a long history, 3500 BC. That is, most of the world's population relies upon natural plants for cure of ailments, and phytoconstituents present in the medicinal plants are responsible for the pharmacological activity, and these phytoconstituents can be classified on the basis of their chemical moiety. Objectives. After studying this unit, you should be able to understand the importance of pharmacognosy, classify the phytoconstituents present in the plants, explain various techniques of extraction, isolation, and purification of crude drugs, and explain the various chemical and spectroscopic methods for characterization of phytoconstituents isolated from plants. First, pharmacognosy. The term pharmacognosy is derived from the two Greek words pharmakon, meaning drug, and gignosko, means to acquire knowledge of. So, the term pharmacognosy was introduced by Sedler, a medical student in Halle, Germany, in the year 1815. A number of definitions for the term pharmacognosy are used, which are as follows. Pharmacognosy is defined as scientific and systematic study of structural, physical, chemical, and biological characters of crude drugs along with their history, method of cultivation, and collection and preparation for market. Pharmacognosy serves as a link between the following: pharmacognosy and medicinal chemistry, pharmaceuticals and basic sciences, and Ayurvedic and allopathic systems of medicines. So it is a link, the study of pharmaceutical products, that is pharmacognosy and medicinal chemistry, pharmaceuticals and basic sciences, and Ayurvedic and allopathic systems of medicine. History of pharmacognosy. The history of herbal medicines is as old as human civilization. Indian history of medicinal plants is taken back from 3500 BC. A large portion of Indian population depends upon Indian system of medicine. Ayurveda, which have well-known treatises in Charak Samhita and Sushruta Samhita. Then, scope of pharmacognosy. Pharmacognosy as an applied science which played a crucial role in the development of different disciplines of science. The knowledge of plant taxonomy, breeding, pathology, and plant genetics is helpful in the development of different disciplines of science. The technology involving extraction, purification, and characterization of pharmaceuticals from natural resources has signified contribution to the advancement of natural and physical sciences. Classification of phytoconstituents. The medicinal potential of a crude drug is determined by the nature of constituents present in it. The plant drugs chemically consist of mixture of organic and inorganic constituents known as phytoconstituents. The phytoconstituents of therapeutic importance can be classified into following main groups: carbohydrates, glycosides, tannins, and phenolic compounds, proteins and amino acids, coloring matter, lipids, fixed oils, fats, and waxes, volatile oils, alkaloids, resins and resin combinations, and carotenoids. First, we will come with carbohydrates. Carbohydrates are defined as plant products which consist of carbon, hydrogen, and oxygen. The ratio of hydrogen to oxygen is 2:1. Carbohydrates are of wide occurrence in nature and provide means of storage and transport of energy, and also building the blocks of the cell wall. Glycosides. Glycosides are substances which on hydrolysis yield one or more sugar or glycon along with non-sugar aglycon compounds. So both sugar and non-sugar compounds are produced by glycosides after hydrolysis. Tannins and phenolic compounds. Tannins are complex phenolic compounds which are soluble in water and have an astringent and bitter taste. Now, tannins are classified into two groups on the basis of their ability to be hydrolyzed. First group is referred as hydrolyzable tannins, as these can be readily hydrolyzed. Second group is non-hydrolyzable tannins or condensed tannins. Then proteins and amino acids, again important classification. These constituents a major class of natural products of different categories, including albumin, globulin, conjugated proteins, which can be used as drugs. Coloring matter. They are widely distributed in natural products. The majority consist of chlorophyll, anthocyanin, and anthocyanins, etc. Lipids, that is fixed oils, fats, and waxes. The term lipid is used for fixed oils, fats, and waxes. Fixed oils are liquid at normal temperature, while fats are solids or semi-solids at this normal temperature, and chemically they are esters of glycerol with long chain fatty acids. These esters are also termed as glycerides. Now, fixed oils and fats are non-volatile. They are insoluble in water and are lighter than it and form a permanent stain on paper. Volatile oils. Volatile oils are odorous constituents found in various parts of plants. They evaporate on exposure to air at ordinary temperature. As volatile oils are responsible for the essence or odor of the plants, they are also known as essential oils. So it can be found in many plants like inflorescence of coriander, flowers of lavender, fruits of fennel, leaves of eucalyptus, bark of cinnamon, and peel oranges. Alkaloids. They constitute a major class of chemical groups present in plant drugs. Originally, alkaloids mean alkali-like, which are applied indiscriminately to all the organic bases. With course of time, the term alkaloid has altered in significance, and presently it includes mainly the cyclical nitrogenous bases which occur in the plants. Cyclical nitrogenous bases. Thus, alkaloids are the naturally occurring organic substances having a cyclic nitrogenous nucleus exhibiting basic properties and a pronounced physiological actions. Alkaloids are found distributed in various parts of mature plants in seeds like strychnos, in fruits like piper, in leaves like belladonna, in roots like rolfia, in rhizomes and roots of epicac, in corms of colchicum, and in bark of cinchona. Now, resins and resin combinations. Resins are solid or semi-solid amorphous products of complex chemical nature. These are usually obtained as exudates from plants and are considered as end products of metabolism. Carotenoids. Carotenoids are responsible for many or red, orange, and yellow pigments observed in the plant and animal kingdoms. Now, extraction, isolation, and characterization of phytopharmaceuticals. The crude drug containing the active constituents which can be isolated from these drugs by various methods of extraction and separation. First, phytochemical investigation. Phytochemical investigation or screening is the extraction, isolation, purification, and characterization or identification of therapeutically or pharmacologically active plant constituents by using different physical, chemical, chromatographic, and spectroscopic techniques. The first and foremost step in this selection is the selection, identification, collection, and extraction of the plant material. So, extraction. Extraction is commonly employed technique for separation of active substances from crude drugs. It involves the use of different solvents. So, the dried powdered plant material is commonly used for extraction. The fresh plant part used in homogenized or macerated with a solvent such as alcohol, which is general solvent for many potential constituents. So, we can use different methods of extraction. Various methods for extraction of drugs include infusion, decoction, digestion, maceration, and percolation. Isolation and purification of constituents. The isolation and purification of constituents present in extract depends upon the physical and chemical characteristics of the compound to be separated. The physical techniques employed for this purpose are fractional crystallization, fractional distillation, fractional liberation, paper chromatography, thin layer chromatography, column chromatography, high performance thin layer chromatography, high performance liquid chromatography, so on and so forth. So we can see various methods. Now, methods of identification of constituents. The class of compounds can be determined by their response to color test with chemical agents, reagents. The various chemicals tests are used for the detection of following classes of compounds, which we discussed in the previous slide also. Alkaloids, carbohydrates, glycosides, phytosterols, fixed oils and fats, saponins, phenolic compounds, tannins, gums, mucilages, and further. So detection of various compounds is also necessary. Then there is a term called spectrophotometry. Ultraviolet and visible spectroscopy, infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance spectroscopy. So, by spectroscopy, also we can absorb many plant products. Okay, so we have finished this last unit also. So, any doubts till now?
No, sir.
No doubt.
Okay, then I will take your leave. Thank you for your patience, listening patiently, and we will meet in next week. One class is left. Mine one class is left. I will take in next Wednesday. Till then, Dr. Shivashis will take the class on Monday and Tuesday, and on Wednesday, I will take the next remaining class of this unit. Okay.
Okay, sir.
Okay,
Oh,
sir. Okay, sir.
okay. Thank you so much.
Thank you, sir. Thank you.